Welcome to Chapter 7, Oxidation Reduction Reactions. The driving force for oxidation and reduction reactions are the transfer of electrons, and these are often called redox. You can't have oxidation without reduction, so oxidizing is losing an electron, and reduced is gaining an electron. There's a couple of mnemonic devices. Oil rig is oxidation involves loss, reduction involves gain. Another popular one is Leo says Gur. Losing electrons is oxidation, gaining electrons is reduction. It doesn't matter if you use one or the other or perhaps something else, just as long as you can remember. This is the oxidation reduction reaction between iron 3 oxide and aluminum. So here's a little graphic. Oxidation, one element or compound is losing electrons, and they have to be gained by something. The electrons just don't go out into the universe. There are four types of redox reactions: combustion, synthesis, which is also called combination, decomposition, and single replacement. These are different than the double disc because we do not have to predict states. The driving force, as I said, was the transfer of electrons, and a lot of times oxygen is involved, hence the name oxidation. Let's start with combustion reactions. That's what we use for our methane gas in the Bunsen burner, and oxygen is always one of the reactants. If you look, carbon dioxide and water are always the products. So you can have some sort of hydrocarbon and oxygen, and you're going to get carbon dioxide and water. I mentioned that these are hydrocarbons because they have hydrogen and carbon. If you drove anywhere in a vehicle today, likely had a gasoline engine, and so octane and oxygen underwent combustion, putting off water and carbon dioxide. Which of the following is a combustion reaction? If I look at D, it has a hydrocarbon, oxygen, and the products are water and carbon dioxide. Pause the video and write a balanced reaction between propane and oxygen. Propane is given to us. Did you remember that oxygen is diatomic? What are always the products for our combustion reactions? Carbon dioxide and water. And lastly, I balance the equation. Balance these combustion reactions. The first is combustion of methanol, so I write the reactants. This time I have an extra oxygen in here that I need to make sure I take into account once I balance. But the products are easy because they are always carbon dioxide and water. The last thing I need to do is make sure that my equation is balanced. If I look at respiration of sugar, this is how our cells obtain energy. So I'm going to start off with sugar and oxygen, remembering that it's O2. Easy enough to predict my products. This hydrocarbon also has oxygen in it, so when I balance, I need to take that into consideration. We can look at combustion, and we know that it has oxygen, and for us, it'll be just hydrocarbons. We're going to always look at complete combustion, where the products are carbon dioxide and water. But I want you to be aware that there is incomplete combustion, and that produces carbon monoxide and water. And so this is why we have carbon monoxide detectors if you have, for example, a gas furnace. I'd also like to point out that these subscripts are just generic placeholders, indicating that any type of hydrocarbon can undergo complete combustion or incomplete combustion. If we look at the carbon monoxide detectors, there are types that look like hemoglobin, and so when carbon monoxide bonds with them instead of oxygen, they become lighter, just like our blood cells. We have semiconductors. These use electronics when the carbon monoxide molecules react with the sensor in a redox equation. That allows the energy to go through, and it sets off an alarm. Lastly, we have electrochemical, where we have electrolytes. We have an ion conductor, and if carbon monoxide bonds with it, it transmits electric and an alarm goes off.